Okay, hi. This is chapter 14, which is about gases, and my goal for this video is to not make a bunch of noise in the background. Everybody's working on stuff. This is a really cool chapter. I do wish we could do the labs in person, but since we can't, here we are. We only have 3 slides for this screencast. So, some properties of gases is what we're looking for. We are not talking about the kinetic molecular theory. So you may remember there were some points on that gases haven't, their volume, gas particles volume is negligible and they have elastic collisions, all of that. That is not what we're talking about. We're talking about broader categories here. Like, for example, they have indefinite volume, which you could say they take the volume of their container, which is to say that you don't ever have, like if you have 4 liters of gas and then you take it out of its 4-liter container, it will become the volume of the container itself. It doesn't have a definite volume. It also does not have a definite shape. You can't say that your sample of gas is the shape of a pencil, for example, like you could say with an actual pencil, which is a solid. Okay, we also know that they have an incredibly low density, often about 1,000 times less than that of the liquid form, and they are compressible, which is related to the indefinite volume. Of course, a lot of these are just derivatives of the same basic properties. And lastly, the one thing that we'll say is that they exert pressure, okay, on their containers. All right. So there are several quantitative ways that we can describe a gas. Those were all qualitative. For example, and for each of these, we're going to say what the symbol of it is, as well as the unit. And remember that the symbol is what goes into a generic equation. For example, F equals ma. Those are symbols, right? The unit goes with a number to make it a measurement. Okay. We can describe a gas in terms of its pressure. The symbol for that is what? Good. P, and the unit, there's lots of units, atmospheres. Okay, those are the most common ones. Just FYI, millimeters of mercury is sometimes also called torr. Can you think about why that might be? Because the man who made the first barometer was named Torricelli. Okay, so 760 millimeters of mercury is the same as 760 torr. We also have PSI, which is less common. We have pascals, which is less common. Bar. The internet will use inches of mercury, like weather websites for atmospheric pressure. Okay, lots of options. Okay, we also have volume can describe a gas. The symbol would be V, capital V, and the unit will always be liters. Of course, there are other units of volume like milliliters and centimeters cubed and different things, but we'll use liters always. Okay, what's another one? You can talk about a gas in terms of its temperature. Capital T. Unit is either Kelvin or degrees Celsius. But degrees Celsius is bad because it can be negative. And if we're doing calculations that involve changes in temperature, the negatives are going to mess everything up. You're going to get negative volumes and stuff like that. All right, the last thing you can describe in terms of a gas is how much of it you have, which we would describe in terms of moles. Obviously, you could also talk about numbers of particles. We just don't. Okay, the symbol for moles, I don't think you know this. I wonder if you can hear that baby crying. Is N. My understanding is that M was taken, but I haven't really looked into it. And then, you know the unit for that. Okay, last slide for this chapter. So how do these all relate to pressure? Remember that pressure is caused by collisions of the gas with what? Container walls, right? And remember that pressure is equal to force over area. So pressure is determined by the force of the collisions, which is a function not only of the force of each collision, but the total number of collisions. So we could say pressure is determined by the frequency and force of collisions, as well as the surface area over which those collisions are applied. Okay, so then how do these things matter? If you increase the moles of gas, how does that change the pressure? Think about, for example, if you are carbonating a drink, you have a container, it has liquid in it, but it also has some air above it, and if you add a bunch of gas into it, you have more pressure. I mean, that's intuitive. The reason for that being that you increase the frequency of the collisions. Why does the force of the collisions not change? Because the force of the collisions is a function of how fast the particles are moving. And assuming all these particles have stayed the same temperature this whole time, the force of the collisions will not change. All that will change is the number of the collisions, which is the frequency of the collisions. Okay, so if you increase moles, you have more collisions over the same area. So you have increased pressure. Okay, example is carbonating. Well, let's just say adding CO2 to beverage container. And you can even tell, like, when you try to squeeze the top of it, it's incompressible. Well, that's confusing. It doesn't squeeze because it's so full. The pressure inside is really high. Okay, volume. What happens if you have a container whose volume you can change? For example, a syringe. So imagine that you have a syringe and it's closed and it's just sitting there, and then you increase the volume. So you pull the back of the syringe out. How does that change the pressure inside? Well, if you can imagine doing that, you can maybe imagine that it would be hard to pull it out at some point because it would feel like it was being pushed in. The atmosphere is pushing in, and the pressure inside the syringe has gotten less. Therefore, you're having to resist all of the atmosphere pushing in on that decreased pressure. So if you increase the volume, which of these factors over here changes? Good, the area goes up of the collisions over which they're applied, therefore the pressure goes down. Okay? So we'll say increased surface area. Same number of collisions, same force of collisions, different area applied, decreases pressure. Lastly, temp. There's a video online that you are welcome to seek out where some put an aerosol can in a furnace and it explodes and they all yell, I'm assuming, obscenities in a different language. It's like, there's like a flame, it's like a, anyways. So YouTube aerosol can in furnace. And so basically if you have particles in a container and you heat them up, so if you increase the temp, the particles move faster, right? Because they have more kinetic energy. So what happens to their collisions? They become more frequent and they become more forceful. Therefore, pressure goes up. Okay. I'll just search for it right now if you want to hang out. Otherwise, you can be done. Oh, wow. That's weird. Okay, the one I'm looking for is this one, I think. Yeah, no kidding.
Yeah, jetzt ganz ruhig. Das könnt ihr nicht machen. Das ist nicht euer Ernst. Nee. Gut, dass niemand weiß. Silikonspray. Die Dose wird so heiß. Hey, Junge. Das war's. Das war erst die Ruhe vor dem Sturm. Du Scheiße. Ach du Scheiße. Oh Gott.
Don't try that at home.